welcome to lecture number 34, and in our last class I started not a new topic, but the problem was that if you have to solve a differential equation and if the excitation function is not a reasonable function like sin omega t, t square, any functions are reasonable which are we can plot. For example, x t, any function like this is a reasonable function which can be described by some equations, or where this is the time axis and this is the value of the function. And then at a particular time, as you were, suppose you were moving from t equal to minus infinity along t axis and looking at values. So, at a particular time, say t 1, it will have a definite value of x t 1. These are reasonable functions. Okay. For each value of time, you have some functions. But if your differential equation is of this type, for example, dy dt plus a y, first order differential equation, this is x t in general we were writing, but if x t is an impulse function delta t, how to get y t? How to get y t? This is the thing. That is the question asked, because delta t is a very peculiar function, and to tell you about that, reviewing, I told you that if you have an rectangle, very quickly I will review whatever we learned last time. Suppose you have a rectangular pulse, and this is minus h by 2, and this point is plus h by 2. These are the time, and the height of the rectangle is h. Then I told you that the area under this curve, under this pulse, under this rectangular pulse, will be always equal to h into h, 1 by h, is it? The height is, I am sorry, the height is, suppose you make it 1 by h. So, it is a rectangle of width h by 2, and this is also h by 2 h, and height is 1 by h. Area will be h into 1 by h, which will be equal to always 1, no matter what is the value of h, no matter whatever value you choose for h. Now, the next thing I told that okay, this h I will make smaller and smaller, the value of the h I will make smaller and smaller, such that these 2 points will come closer to the origin t equal to 0, this is origin. So, it will come, if you make h smaller and smaller, the height of the rectangle, which is 1 by h, will go up, and these base points will come closer to the time t equal to 0. Then I say, but the area will remain same, 1 unity, because I am still keeping this to be 1 by h. Now, in the limit when h tends to 0, this rectangular pulse will be a very thin strip, and this height of this rectangle will raise to infinity. At the same time, these 2 points will come very closer to the origin. So, under that condition, what I will say that t equal to 0, then this point is 0 minus and this point is 0 plus, close to origin, close to t equal to 0, but not really t equal to 0, but as close as you can think of. Imagination does not prevent us to think as small a number as we please. And under that condition, this height of this rectangle will raise to infinity, 1 by h will raise to infinity, but still that rectangular strip will be there as if, and area under the curve will be 1. So, such a function is called unit impulse function. So, this I discussed last time and denoted by this symbol, which is unit impulse function. And it will be denoted like this. The value of the function delta t will be equal to 0 for t not equal to 0. Any other values of t, the value of the function will be 0. That is, suppose the red one I am using for sketching delta t, it will be 0 for t less than 0 to minus infinity and t greater than 0 to infinity. This will be all zeros. This axis is time axis, but at t equal to 0 something happens. The value of the function will show it by a line and an arrow, because we cannot show infinity in any scale. So, this arrow indicates that it is infinitely large. The amplitude of the function is infinitely large. Therefore, the second thing is no point in writing delta t. I mean, if somebody says one can write delta t equal to infinity at t equal to 0, but what is the point of dealing with such a function, because infinity is not any finite number. But what is true is this: the integration of delta t, area under the curve, delta t dt, integrated from 0 minus to 0 plus, this is 0 minus, this is 0 plus, close to 0 on either side, this integration must be 1. That is what I tried to tell. This is finite, but no point in asking what is the value of the function at above. That is infinite. Okay, what I will do with that number, large number, undefined. So, this is the basis of an unit impulse function. Its magnitude at t equal to 0, well, very large, but I cannot quantify it, infinitely large, and delta t equal to 0 for any value of time. Here it is 0, here it is, red one is the delta t curve, and at t equal to 0 function is infinitely large, but this is true. This is very important. This is true. Now, if such an impulse function is applied to a circuit as input excitation, how to find out the currents, or how to essentially that circuit in general will have energy storing elements. Therefore, how to solve a differential equation. Okay? That is why I told that this differential equation, suppose dy dt plus a of y is equal to delta t. If such a situation occurs, then the solution due to natural function will remain same, that is y t its solution, we know it will be a into e to the power minus a t, that is there, because characteristic root is minus 1. But what about the solution due to forcing function? I was earlier telling that if the right hand side is x t, then I told it will be a linear combination of x t and its higher order derivatives, is not, up to infinity, that is what I was telling. But in this case it will not be like that. So this part is applicable only to reasonable function whose derivative exists at different values of time, because linear combination of the function and its higher order derivatives. That is, in this case I should not write the solution will be delta t plus k to delta t delta dot plus delta double dot. No, it will not be like that, because it cannot be, because of the simple fact, because delta dot t, what does it mean? If time permits I will explain, but there is no delta dot t on the if such thing exists, it will be difficult, it cannot be like that. So, we have to find out the solution with open mind, and I will be doing it in this fashion. Therefore, this is not correct here, the solution we do not know. So, y t, this part of course will be there. Achha, now, to approach this problem, before that I will tell you one very interesting thing. Any reasonable function, okay, for example, x t, a function x t. We know what do I understand by x dot t. If I ask you to sketch x dot t, I will be able to sketch. I will calculate the slope at various points, and then I will be able to sketch x dot t. Try to follow me. Okay. For example, if it is like a signal, suppose the signal is like this, say the function x t is equal to t square, then this is x t. We know from our school level knowledge that to sketch x dot t, you have to differentiate this. This will become 2 t and it will be like this. So, this was from minus infinity to plus infinity time axis, this is x t equal to t square parabolic, and if you differentiate it, it will become 2 t like this, also negative side, is not, slope will be negative. So, this is 2 t which is equal to x dot t, got the point. So, any function given, we can find out x dot t. Next thing, I will pose another problem. Suppose you have a unit step function, for example, I told you about unit step function last time, very simple, which is equal to u t equal to 0 for t less than 0 and u t is equal to 1 for t greater than 0. Okay. This is your time axis and the value is, this is called unit step function, unit step function. Now, if I ask you differentiate the unit step function, what will be your answer for all time t? So, what will be d u dt is what? I want to sketch it here, d u dt. Obviously, this portion is very simple, this will be 0 all the time. So, its differentiation of this constant number 0 is 0. So, d u dt will be 0 like this. At t equal to 0, I am not sure, and for t greater than 0, it is once again constant. So, d u dt will be once again a constant number like this. Got the point? So, I am sketching d u dt with this green color. So, this is 0 0, and about this point we will tell okay, it has got a discontinuity, because the jump from 0 to 1 means it is a discontinuity. From this value 0 to 1, it has, this jump has taken place in no time. Therefore, slope is infinitely large like that, and we will say, we cannot say it is very large slope. But after learning the impulse function, I will say that there will exist an impulse at this point. Why? That I will tell. Now, before I proceed, I will tell very slowly, so that you do not miss any point. So, now I will tell you one important thing. You must be knowing that any function drawn, for example, I draw one function like this, a voltage pulse like this, x t is like this, and this is time axis, this is 0. And this is suppose 1, this is 1 and this is minus 1, and elsewhere the function is 0. Now, this function x t here, since x t is equal to x minus t with a negative sign, it is called an odd function. You must be knowing, I will be telling very odd function it is. The value at any time t here x t, and at t and at minus t it will have same value, but with opposite sign. So, when such a condition is applicable, it is called an odd function. You can have several odd functions. At any positive value of time, whatever is the ordinate, corresponding negative value ordinate will be same. Similarly, there may be an even function. So, odd functions will be there, you can sketch many of them. Now, similarly, a function which is having, suppose I sketch a function like this. This is suppose 1, this is half, this is minus half. Suppose it is a function like this. This function, whatever is this function, that function I am calling x t. This x t is an even function, Why? Because the value of the function at any time t is same as the value of the function at the corresponding negative time. These two are same. Therefore, because x t is equal to x minus t, this is the property an even function will have, and it has to be true for all the time t, that is true. Similarly, odd function, it is to be true for all the time t. So, this is simple example of even and odd function. Okay. Now, in general, functions may not be either odd or even. For example, a function, I sketch it like this. This function x t, the third x t, this function, this x t is neither odd nor even, neither odd nor even. This function is neither odd nor even. Why? Because it does not satisfy this at t equal to t. Suppose any time you choose, this functional value at t is this, and at the corresponding value, the value is not, this is not equal to this height. So, it is neither odd, and also it is not even, because negative of that should come, but it is not coming. And similarly, x t is not equal to x minus t. Therefore, this function is neither even nor odd, and most of the functions will be like this in general. However, any function which is neither odd nor even can be broken up into two functions as sum of two functions, of which one will be even, another will be odd. What I mean to say is this one: any function, this you write down, any function, any general function can be expressed as sum of an even function and an odd function. What does that mean? Suppose x t, any general function x t. Therefore, what it is telling me is this: x t can be expressed as sum of an even t plus sum of an odd t. Then the question is, if I know x t, can I find out the even terms and the odd terms? Yes, I can, because I will apply the property. For example, replace t by minus t, then x minus t on both sides, I will write it x even minus t, replace t by minus t on both sides, x odd minus t. this I can do. But since this part has to be even, these two must be equal, or x of minus t will be equal to x even t. This I can write. Since this is even, these two are equal, and since this part is odd, x odd minus t will be equal to minus of x odd t. It has to be, that is by definition. So, so this equation is x odd t. So, we have got now these two equations 1 and 2. X t is known, so x minus t is also known. Therefore, add 1 and 2, 1 plus 2, it will gives you x even t this plus this, that is this equation and this equation. If you add, it will give you x even t as x t plus x of minus t divided by 2, and you maybe many of you know it, but x odd t will give you x t, subtract 1 minus 2, subtract, and it will give you x odd t, as if you subtract, it will give you x odd x t plus minus of x of minus t divided by 2. Very useful results these two are. Therefore, given any function, I can find out the even and odd part very easily. Now, why I spent so much time on this? Because of this fact. Now, because what I was trying to tell, I want to find out the this was my problem. Ut is given, I want to find out du dt, that was the problem. So, I come back here. So, problem was, once again I redraw better. This is an unit step function. This is magnitude 1 and this is your time, this is your 0, and ut we know it is 0 everywhere, for t less than 0 is equal to 1, fine. Now, this function which is ut, is it even or odd? Neither even nor odd, because at any t you take, it is plus 1, negative t it is 0. So, it is neither even nor odd. Therefore, this unit step function can be broken up into its even and odd part, and its x t u t even, its even part will be how much? U t plus u minus t divided by 2, that is what we learned. And what is u minus t? U minus t is 0. So, it will be half. So, u even t is half, and u odd t will be equal to u t minus u minus t divided by 2, is it? So, u odd t will be how much? As signum t. So, it will be equal to signum t. For t greater than 0, it will be plus up, and for t less than 0, it will be minus up. So, in other words, you can also visually it is more attractive, that is the even portion is half for all time t. This is u even t, and u odd t will be equal to minus half here and plus half here. You see, you add these two, you get half 1, this is also half, and that is this part, and this part it is plus half, it is there must be minus half here. So, this is the u odd t and it is odd, you see, plus half, same time it will be minus half. Therefore, sum of these two gives you the unit step. So, I will write it that u t therefore, is equal to this curve plus this curve, that is u even t plus u odd t. Therefore, du dt will be equal to d dt of this even part, d dt of this u even plus d dt of this u odd. It will be like this. Now, obviously, this first term it is constant throughout, so it will be 0, and derivative of du dt is nothing but derivative of this function u odd t, d dt of u odd. Got the point? Now, what will be the derivative of this function? Derivative of this function will be, for t less than 0 it is constant minus half, so it will be 0, and for t greater than 0 also it will be 0. Is not, that is what, at least about these two times I am sure, so simple, constant d dt of half is 0 and d dt of minus half is also 0, this will be the thing. Problem is here, here is a discontinuity, from minus half it is jumping to plus half. For this part contribution will be 0 all along. Now, the question is what should I do with this one? I am telling you, first I will tell the result, then establish that this derivative will be an impulse here, unit impulse. Why? Got the point? The derivative of this function, I am telling that it will be an unit impulse, because change has taken place from minus half to plus half in no time. Let us see that. So the, and what I know that, for example, this function u odd t, I want to find out this d dt of this, which happens to be equal to du dt, that we have established. Our original problem was here, from this I got this. Oh, you find out the derivative of u or t, you get du dt. Fine, I have reached up to this point, d dt u dot t. This is the thing I have got. Now, I am telling that this will be equal to an unit impulse, although not proved it yet. Is it correct? Let us see that. If this is true, then you multiply both sides by dt. If this is true, multiply both sides by du or t. Multiply both sides by dt, delta t dt. Then you integrate this function from 0 minus to 0 plus, both sides. Because as you know, delta t infinity large, what can I do? But about one thing with impulse function is sure, 0 minus to 0 plus delta t dt is 1. Now, let us see whether left hand side gives you also 1. So, this integration will simply tell you that u dot at t equal to 0 plus, this integration will be this one only, then put the upper limit, minus u odd 0 minus, and this side I know, and what will be this quantity? This quantity will be, and this side is 1 and this quantity is half. For t greater than 0 it is plus half, for t less than 0 minus half, half minus minus half, and this is equal to indeed 1 equal to RHS. Got the point? So, what I am telling, given a function, if there is a step jump of the function or discontinuity of the function at some point of time, I will say that look here, the derivative of the function at that point where that step jump has taken place must be, there must rise an impulse. Clear? So, I repeat the steps. What I did, this was the unit step function. I first, my problem is to find out du dt is how much. So, first I broken up this function as its even part and odd part, that is the even part, that is the odd part. So, differentiation of ut will be differentiation of even part plus differentiation of odd part. Even part is in any case is constant all along the time scale, minus infinity to plus infinity, that will give you 0, that is 0, then plus ddt of u odd t. Now, u odd t is this minus up and plus up. So, d dt of u odd t I have to then find out du dt, which is nothing but du u odd t divided by dt. These two are same. So, du odd t is what? I am telling maybe du dt you multiply with dt on both sides. Let us assume, okay, but I am not sure, I have put a question mark, maybe it will be equal to an impulse, delta t I have put, okay. Then you multiply both sides by dt, then it will be du odd t is equal to delta t dt, that I have not written. Then you integrate both sides from 0 minus to 0 plus. Left hand side will give you 1, because if you integrate it, it will become u odd t, and u odd t at t equal to 0 plus is up, this is minus up, so this is plus 1, and on the right hand side this has to be equal to 1, and indeed it will be 1 if you integrate this function delta t dt from 0 minus to 0 plus. Therefore, we say that the if you differentiate an unit step function, you will get delta t. So, summary of this whole exercise is du dt is will give you an impulse. So, it was your unit step function here. This is unit step function ut, and below that I sketch du dt. Du dt will be an impulse, unit impulse. So, earlier perhaps if I did not know delta t, no idea of impulse function, I would have simply told okay, there is a discontinuity here. But here now, after cultivating an impulse function a bit, I come to know okay, it is better to show it as an impulse. What is the area under the curve? That is the strength of the impulse, that is 1. Got the point? And what is the unit step function? It is ut. Similarly, you can sketch, suppose you sketch another curve. Say if I ask you to sketch 2 ut, so it will be an unit impulse function of strength 2. This is 2 ut. For t greater than 0, it is 2. And if you differentiate this function, at this point, this 2 is in any way constant, 2 into du dt. So, you will still get an impulse, but you should write it as 2 delta t, is it? So, d is equal to d dt of 2 ut is equal to 2 du dt is equal to 2 delta t. So, impulse function is an important function in circuit analysis, which we will explore it further in the later case, in some later lectures. But for the time being, why I told up to this point is that, for example, I tell you that here is a function, okay, try to understand, a function like this, a square pulse. This is say minus 2, this is say plus 3, and here is a rectangular pulse of magnitude 5, and this is your time axis, this is your 0, and this is your function xt. Got the point? So, value of the function was 0 for t less than minus 2. The value of the function is once again 0 for t greater than 3, and between minus 2 and 3 it is plus 5. I ask you sketch dx dt. So, I will better draw it once again here, so that you. So, this is my time axis. Here is a pulse. This is suppose minus 2, this is suppose plus 3 in time, and this strength is 5. And less than t minus 2 it is 0, greater than plus 3 it is 0. This is your xt. There is no impulse, mind you, xt. Acha, now I ask you what will be dx dt? Dx dt. Okay, dx dt for t less than minus 2 has to be 0 because it is 0. For t greater than 3, it is to be 0, it is 0. Dx dt I am sketching, this is xt. And between minus 2 and plus 3, it is 5. So, that will be also 0 because constant value. But here lies the discontinuity. At t equal to minus 2, in no time it jumps from 0 to plus 5. So, I will expect then there must lie an impulse here, positive impulse of strength 5 delta t. You must understand this. Similarly, at t equal to plus 3, there is a discontinuity from plus 5 to 0, and I will say at t equal to 3, I am sorry, do not write it as 5 delta 3, but it will be some delta function here, minus 5 delta. This requires a slight modification because delta t is an impulse sitting at the origin. You must understand. Delta t, what I did, it was sitting at origin. You must be knowing. So, if I ask you sketch delta t minus 2, what you will sketch? The same function shifted towards right by an unit 2. So, here will lie delta t minus 2, is not shifted. Any function xt shifted given a right shift. So, if you change the argument t to t minus 2, it will give you this one. Therefore, here this integral delta t minus 2 dt 2 minus 2 plus will be 0. Got the point? Therefore, this function, this is a shifted delta function. So, it will be a negative value 5 delta, and I must write t minus 3. Similarly, this function I must write delta t plus 2. It is given a left shift with respect to origin. Therefore, dx dt of this rectangular pulse will look like this, consisting of 2 impulses. More about this we will discuss further, because you know, if you know a function xt, if time is shifted t minus a, the waveform itself shifted to right by an amount a, like that. So, anyway, so with this I stop here, and in the next class we will solve an RL circuit, response of the RL circuit, that is current when the excitation is an impulse. Thank you.